Hello, everybody. It is a great pleasure to have you all here with us for this afternoon session of our Granular Matter Day, Granular Materials Day, in the 14th summer workshop in mathematics at the University of Brasilia. So it is a great pleasure for me to introduce our next speaker, Nicolas Taberlet from University of Lyon and École Normale Supérieure de Lyon, who's going to talk to us about granular segregation in rubble pile asteroids. Nico, thank you very much for coming. You can please start your talk.
Okay, well, thanks, Yuri, for the invitation. So as you said, I'll be talking to you about granular segregation in the rubble pile asteroids, and that's a work done mostly by my PhD student who has now graduated, Jérémy Sautel. So what we are interested in is a certain type of asteroid called rubble pile asteroids. And here's two examples of those, one called Itokawa, and the other one called Bennu. As you can see with the scale here, they are small bodies. Itokawa is something like 500 meters apart, and Bennu is a little bit smaller, around 300 or 400 meters. And those two examples were taken by missions from different agencies. From the Japanese, from NASA, from the ESA as well, that have recently visited those asteroids. So they consist in an assembly of grains with no cohesion. That is not always the case. Some asteroids have cohesion, some have ice between the grains, but some don't. And in this case, in rubble pile asteroids, grains are simply held together by their own gravity. However, those bodies are not completely static, and they may rearrange in the micro-G environment that they have. So there are several possible causes of internal motion that would cause local rearrangements. First of all, there can be tidal forces, especially when the asteroids are closer to Jupiter or the Sun. It could be, although it's probably very unlikely, that there are collisions with smaller bodies, and those asteroids are so small that it's probably a rare event. However, there's something known as the Yorp effect, which is a constant increase in the rotation speed due to solar irradiance. I'll say a few words about that. Those bodies, as you can see, are not spherical, and the solar irradiance induces a torque on them, which then makes them spin faster and faster. And as a consequence, the centrifugal forces can induce failure and internal motion. So one striking feature of those asteroids is that the grains at their surface are not uniformly distributed. And instead, the distribution is inhomogeneous, as you can see on this picture, which is a closer view of Itokawa. There are sea of small grains that can be below 1 millimeter, and there are regions of much larger grains, typically 1 meter, as you can see here on the left. So the question we're asking is, can granular segregation explain this? So let me say a few words about size segregation on Earth. And what I mean on Earth is in a lab. So granular matter, when you take small grains and large grains, they tend to segregate, that is to say, to separate. Small grains will gather together, and large grains will gather in other regions. And that happens under a variety of conditions. The first example I've shown here is segregation under horizontal vibrations. So you take a cup, a dish, in which you put small grains and large grains, and you shake it horizontally. And as you can see on picture C, the large grains have gathered, and the small grains have gathered as well. That is the even more famous Brazil nut effect, segregation under vertical vibrations. If you start with a mixture of small grains on the top and large grains at the bottom, as you can see here, and you shake that vertically, you end up with the opposite segregation, and this is the steady state here. Large grains tend to rise to the surface, whereas small grains tend to sink to the bottom. And finally, I want to mention segregation in granular flows. This is a very famous example of those stripes that are visible, studied by Maxey and Gray as well a few years ago already, in which a mixture of grains will segregate when it flows down a pile. So like I said, the questions we are asking is, can the classical segregation mechanisms that are well studied on Earth explain the size inhomogeneities seen in asteroids? So in other words, can that Brazil nut effect on the left explain the observations on an asteroid like Itokawa? This idea has been addressed, this question has been addressed in the past. There's been some previous work a few years ago by Pereira and co-workers, numerical work like what we like I'm about to present, of shaken asteroids. And as you can see on these pictures, initially you have a well mixed state, and after a few days, in their case, they measure the time in days, one can observe some segregation. At the surface, there are fewer large grains that appear in yellow here. This is an internal view of the simulation. However, in those simulations, there were very few particles, and especially very few small particles. Actually, there's the same number of small particles as large particles, but they are being much smaller. The total volume is very low, and there are very few grains overall. There's been another study 10 years ago by Paul Sanchez and co-workers, in which they have studied an asteroid under collisions. The results are also very interesting. As you can guess on this picture, the large grains, in that case, they appear in white, are denser at the surface of the asteroid. However, what they've studied here is a gaseous state where the medium is highly agitated, including inside the asteroids. So it's not a dense state as it is obviously the case for an actual asteroid. All right, so let me present the numerical methods. What we have been using is soft sphere discrete element methods, something that has already been described in this morning session. So I won't go into details, but the idea is that one can compute mechanical forces between deformable grains that are in contact, grain A and grain 1 and grain 2 on this picture here. There's a repulsive force here acting between them, which is given by Hooke's law for elasticity. There's some dissipation in the collisions. As we all know, when you drop a tennis ball on the floor, it doesn't bounce back as high. And we use the Hamilton-Coulomb's law for friction for the tangential forces acting between those grains. So as we know all the forces and the torques acting on all grains, we can simply integrate Newton's equations in order to compute the positions and velocity and the forces of all grains at regular time intervals. So a little more details about what we've been doing more specifically. What I will present first is 2D simulations. So on the left, this is how we initiate the asteroids. It's a minor detail, but all the grains are randomly placed on concentric rings here. And after that, we turn on the gravity field. So the gravity field here is known. We assume that the asteroid will remain spherical, or in this case, circular. And that allows us to exactly predict what the asteroid gravity field should be. And as you can see, it's linear. It increases linearly from the center to the outside of the asteroid. And of course, outside of the asteroid, it would decrease as 1/r squared. So this is very important. We don't compute the self-gravity between each grains, and this is done in order to save computational time because, well, there are numerical tricks that you could use, but it is unnecessary as long as the asteroid remains spherical or circular. So, sorry, I should have said that after that first phase, all the grains collapse to the center, and due to the friction and the inelasticity, the asteroid quickly comes to rest. So now what we've been doing, as I've explained, we were trying to mimic the Brazil nut effect in this specific geometry to see if it can explain the observations. So the process in our simulation is that we start with an asteroid at rest, and for a short time, we reverse gravity. So instead of the grains, instead of being attracted to the center, they're pushed away from the center. Of course, this is entirely artificial. This is not all what's supposed to happen in actual asteroid, but this is exactly what happens when you shake granular media up and down. So after that very small expansion phase, the grains collapse again, and we wait for the asteroid to come to a complete rest to do the next expansion. And I will be referring to this as an expansion or a perturbation or maybe a quake, because it resembles an earthquake. And typically, as you can see here, this is the maximum expansion, so it's only a few % of the radius of the total radius of the asteroid. So in summary, we have a few control parameters. We can, of course, change the size and the mass of the individual grains. We can also change the size of the asteroid. We can also change the intensity of the gravitational field. Mechanical properties such as the friction coefficient, the inelasticity, so the ratio of the final speed over initial speed for a binary collision. And finally, and very importantly, we can also change the duration of the expansion, which gives the injected energy. The longer the expansion, the more energy the asteroid will have when it collapses back. So the first result is that it works. As you can see here, these are times, well, these are snapshots of the simulations after 500 perturbation expansions, 1,000, 2,000. And you can see that starting from a really well-mixed initial state, we end up with a perfect granular segregation. So the first result is that, yes, indeed, the Brazil nut effect works. It's not obvious because in most cases, the Brazil nut effect is due to convection within the material. And here, there being no sidewalls, convection is not possible. And as we actually checked that it was not observed. But instead, there's some dynamical sieving, meaning that the small grains find their way through the large grains down to the center, and whereas the large grains rise to the surface. So this is, of course, satisfying to us, but it's already an interesting result that in that 2D experiment, that 2D simulation, I should say, with a known gravitational field, it does work. So we can quantify the segregation, and we have defined a degree of segregation here, psi, which is simply the ratio of how far the large particles are from the center of the asteroid to the average distance. We can normalize this quantity so that, sorry, it's all messed up here, but so that if psi is 0, means that the asteroid is fully mixed. If psi is 1, it means that it's perfectly segregated. And we can plot this, psi as a function of the number of expansion cycles for the previous simulation that I've shown. And a few things can be said. First of all, it reaches a steady state. In this case, typically after something like 500 or 1,000 quakes. There is an excellent segregation in the steady state in that specific case. So with this specific set of parameters, high friction, 0.5 restitution, and an expansion time of 1.25, which is meaningless in random units. But as you can see, it reaches a segregation degree of almost 100% here, 1. What we can see also is that the data can be empirically fitted with a simply exponential decay law, which allows us to define and measure a segregation time tau and the final degree of segregation psi infinity. To convince you that this fit is actually relevant, I've plotted the same data here on a semi-log scale, and you can see a pretty nice straight line. And this is how we fit the data to observe those values. So in this specific case, we get something like a 0.96 or 97 for the final degree of segregation, and the typical segregation time of 300 quakes. Well, of course, I've shown you an example that works really well, but it's not always the case. For the same parameter, same set of parameters, except with a lower friction coefficient, 0.5 in that case, we can see that, first of all, the segregation takes longer. After about 2,000 expansions, it has not reached a steady state. We can see that overall, the segregation degree is not as high, so it's less good, with a typical limit of something like 70% of the ideal segregation. And we can also see that there are large fluctuations in the steady state. So I want to emphasize that for depending on all the parameters that we can play with, the segregation can be more or less effective and faster or slower. All right, I want to quickly mention that the phenomenon is robust. If we start from those three initial states, so we start with a mixed state, a perfectly segregated state, and an inversely or segregated state, we can run the simulations, and we find that all three initial conditions seem in that case to converge to the same value within a given time. So there's no dependence on the initial configuration, and the system will end up in the final state that it's happy with. Okay, so a few words about when segregation occurs. So what I've plotted here is a zoom into a given perturbation. In that case, about roughly 100 expansions. So this is the radius of the asteroid. As you can see, it expands, and then gravity is turned back on, so it comes back. All the grains collapse, and when they collapse, they bounce against each other and quickly come to a rest. And if now you look at the degree of segregation, you see that pretty much nothing happens during that first phase. Of course, everything is expanding, so there's no relative motion between the grains. And when they collapse and rearrange, you can see a jump in the degree of segregation. Of course, in that case, it's a very small jump, less than 1%, because this is just one expansion. But this is precisely when the segregation mechanisms occur. What I've shown here is the final degree of segregation and the segregation time as function of the inelasticity, and more specifically as the function of the coefficient of restitution. Well, interestingly, you see that there's barely, within error margins, there's barely any influence. So there's no noticeable trend that remains true for all values of the friction, of the size of the asteroids, of the mass, of anything. So in the rest of the work, we have simply decided to keep the typical value, a typical restitution of 0.5, but it doesn't make much difference. However, there's of course a very clear difference on the expansion time. Like I said, if the expansion time is very small, you give your asteroid a small perturbation, a small quake, not enough energy to do anything. And the typical time here clearly decreases with tau. However, what I've plotted here is a variety of parameters, friction going from 0.3 to 0.8, gravity going from 0.1 to 2, and the data doesn't really show a very clear collapse. And this is because when you compute the total energy that was given to the system by the expansion, you get the following formula. It's proportional to the mass of the asteroid, to its radius, and to a typical energy, which is a function of the expansion time, of course, but also gravity. So it seems from this formula that T is not the only relevant parameter, but T times root square of G would probably be more relevant. So this is what I've plotted here. Now it's the same data as before, but plotted as function of T times root square of G. And you do see that all data with a variety of gravity, variety of friction, collapse on the same master curve. So for the segregation time, of course, as expected, for higher amplitude, for higher expansions, it takes less time to occur. However, there's something very interesting for the final degree of segregation. There seems to be an optimal expansion to have a good segregation. As you can see here, for very low expansion times, that is to say, a very gentle perturbation, pretty much nothing happens, and the segregation mechanisms are frozen. On the other hand, if you shake the asteroid too hard, then it gets mixed again at every expansion. So there is this is interesting result that is an optimal set of parameters for which segregation seems to be the best, seems to be working the best. What I've plotted now is the influence of the friction coefficient. Again, this is the final degree of segregation as function of mu for a variety of parameters. And you can see that in general, the greater, well, the higher the friction, the better the segregation. However, this time there's something interesting going on with the segregation time. And for all values of the expansion time, you do see that there is a value around 0.3 for the friction, for which the segregation is much lower. You can see on the blue curve, for example, that it ranges from 10 to the 3, so that's 1,000 to 100 times more. So it takes 100 times longer for the segregation mechanism to occur here. This was not expected. This seems to be pretty much the case for all values of the parameters that we've used. And we can try to understand this by looking now at the average grain displacement. So we've defined the following quantities here. D is simply the displacement of a single grain between two consecutive expansions. dn, sorry, I should have said di. D is now averaged over all the grains. And we have also averaged this over the segregation time. So in the initial steps, in the first initial steps where before the final state, I should say. And now if we plot this average displacement of all the grains as function of the friction coefficient, we can see that there's a clear minimum at around, again, mu equals 0.3. So it means that for this value, and we don't really have an explanation for why at the moment, but for this value, this is when the motion between the grains is the smallest, which explains why it would take longer, of course, for the segregation to occur. Also, what we can look into further details, and what I've plotted here is the difference between the displacements of the large grains and that of the small grains. And you can see that this is negative before 0.3 and positive on the other side. And 0.3 is exactly when the small grains move, when their motion within the asteroid is the same as that of the large grains. Again, meaning that the segregation would be more difficult. All right, in the last few minutes, I want to talk about a secondary instability that we've observed. So, as I said, we observe radial segregation. So after a few expansions, well, more than a few, in that case, almost 5,000, you observe that most of the large grains are on the outside of the asteroid, but also there's some inhomogeneity at the surface. You can see here that there are regions that are much denser in large grains, and here, for example, regions that are more dense in small grains. I've highlighted those regions here. And the question, of course, is, well, the interest, I should say, is that it's reminiscent of Itokawa. As I pointed out in the introduction, there are regions where you have a sea of small grains here, for example, or here, and other places where you end up with a greater density of large grains. So we can be a little more quantitative and measure the surface density or the surface concentration in large grains or in small grains. And we've divided here the asteroid in its inner core and near the surface. So in the inner core is half the radius, whereas the second half of the radius is labeled the surface. And what I've plotted here is a space-time plot or a time evolution of the surface concentration in large grains. So this is the position around the asteroid in degrees. And this is the time or the number of expansion cycles. And as you can see, we start from an initially well-mixed state, of course, and after a while, there appear seas of large and small grains. So this is a way to quantify the results that we've observed, but the dynamics here is very rich. You can see that after typically in this line here at 4,000 or 5,000 cycles, you end up with 1, 2, 3, 4 seas of large grains. Whereas if you go all the way to 10,000 cycles, you have only 1, 2, 3 of those lobes. So there's an interesting dynamics that has been observed in other segregation mechanisms in the granular material. And this is ongoing work, so I don't have much more to say now, but there's a student working on it at the moment. So this is to be continued. I want to finally say that we've also performed numerical simulations of 3D asteroids. Interestingly, it works really well as well. So as you can see on the left, this is the initial state with a mixture of large grains and small grains at the surface. And after, in that case, only 400 cycles, the segregation is already really good. You end up with a lot more large grains at the surface, as can be seen here. One interesting result also is that the segregation time is much faster in 3D. And this is probably explained by the how easy it is for grains to move in 3D rather than in 2D. Small grains can go around large grains, whereas in 2D they have to go in between. We can also take a cross section, in other words, a simple inside view. So this is the initial state and the state after 400 expansions. And there's something interesting. Not only is there some nice radial segregation on the surface here, you see a nice ring of large grains, but also you see an inner core of large grains as well. So the segregation is different from what we've seen in 2D, where the core was almost entirely made of small particles. In that case, there is a core of large grains, then a shell of small grains, and even further, another sphere of large grains. So again, this is still ongoing. We can also plot the degree of segregation in the 3D simulations. You can see that, like I said, the segregation time is much less. Typically, in this case, within 200 expansion cycles, the steady state has been reached, but it's not that steady. And after a while, it even vanishes. For low friction, this is what we get. For high friction, we get pretty much the same dynamics. It takes a few hundred cycles to reach a steady state, which then collapses and even oscillates. And what we can do now is, again, look at the distribution at the surface. So after 100 cycles on the left, so this is if you want a map of the surface, nothing happens. But after 800 cycles, we do see that there is again some angular segregation with two regions of large or small particles in this case. And we can take a look. If we take a cross section, in that case, after 800 cycles, you do see that there's a nice lobe of large particles, another one on the other side, and inside there's still a core. And we've observed that those oscillations here correspond to exchanges between, or migration between of large grains between all three regions here, between this lobe, the inner core, and that lobe. Again, this is still ongoing work and it should be continued. I want to quickly, and this will be my last slide, mention that we've also tried, and this is still ongoing, to do 2D experiments in which large grains and small grains are placed in a parabolic profile, which mimics the radial linear gravitational field. We shake it up and down, and we try to observe segregation in that state. And again, this is still ongoing, and I hope I'll have more to tell you next time. So in conclusion, I want to say that in our simulations, we've seen clear radial segregation in both 2D and 3D asteroids under vibrations. The degree and time of segregation depend on the friction coefficient, the gravity, the intensity of the expansion. However, they do not depend on the inelasticity. The dependence on the friction is related to the displacement of the grains. And also, we have observed a secondary instability, regions of large and small grains at the free surface, both in 2D and in 3D, which are similar to observations made on actual asteroids. And I want to point out a publication that came out last year if you're interested in learning more about this. With this, I'd like to thank you for your attention.
Thank you very much, Nicolas, for this very nice and exciting talk. So we have some time for questions. Do we have questions there? So I think Lou has a question. Go ahead, Lou.
Hi, Nicolas. This is very interesting results. I just want to get more information about the problem. I wonder when you have this expansion and then bring back by gravity, the particles are actually in a pretty dense state or dilute state. And then is there like a cycle? Sometimes it's dilute and then segregation occurs faster and then they become dense, it become slower, or is that not the case? And also because of the friction had so much influence on the results, so I just wonder whether it's collision driven or is there some frictional force as well?
That's a good question. I should say that the asteroid is always dense. It's not the case I showed on the initial slide is extreme, and this is the maximum. Sorry, if you can see this. This is the maximal expansion that you get. After that, they collapse again, and the rearrangements are always very small. One grain between two cycles or within one cycle cannot travel any further than like 1/10 of its radius. So it's not a very agitated media. It's just very small displacements at every expansion. So I agree with you that if we were to give it a lot more energy, then we would be in a dilute state and the mechanisms would be different, but we remain within that very dense state all the time.
I see. So in this case, can we say it's a little bit like the cyclic shear case where you still have some little kind of deformation and then there's gravity pulling particles down?
Right.
Okay, thank you.
Thank you, Lou. Do we have more questions? I think Chris has a question. Go ahead, Chris.
It looks like I can't turn on my camera, but I'll just talk.
No worries.
Thank you. So I wondered, maybe this is something which is you'll just be able to talk about it in the future rather than now. But with this non-axis symmetric segregation you're getting, do you think that that is due to some kind of recirculation cells, like convection cells, or do you think it's a granular process which is segregating the material along the surface?
Yeah, that's a good question. I don't have the slide to show here, I think, but we have checked that it's not a convection cell. We have tracked the motion of all grains over longer times, over short times, over everything we could, and it seems to be only not random motion, of course, because they migrate towards the surface, but there's no overall convection. And what I believe, and it should be investigated more, is that it's closer to what happens here in this first example, where segregation under horizontal vibrations occur. As you said, and as I mentioned quickly, it is well known that for the Brazil nut effect, in most cases, experimentally, the major effect is convection. So the large grains will end up to the surface and then they stay there. But in the case of the 2D system, like this one here, which is shaken horizontally, there's no convection. However, the large grains seem to gather together. And this is due to something known as depletion forces. Typically, in this medium, when two large grains are apart, away from each other, the small grains in between them induce an average pressure, which is entirely isotropic. However, when they get close, there is a lack of small particles between the large ones, which creates a deficit in the pressure and pulls those particles together. And I believe, well, this is just my belief, my intuition, I should say. My intuition tells me that this secondary instability is due to this depletion mechanism rather than a convection. Again, this has to be checked, and we have to perform further studies to prove this.
Interesting, thank you.
Very nice. Do we have more questions? Nico, I have a quick question following up Lou's question. So have you checked the importance of the coefficient of restitution on the results of segregation? And can you say that the flow is more frictional rather than collisional in these granular oscillations, gravitational oscillations that you have?
Absolutely. I would definitely say that. We've checked the influence of the restitution coefficient. Let me show you the slide again. There we go. So from a range going from 0.3 to 0.8,
it's there. Okay, yeah.
There's no influence. And this one thing we've done, and I didn't mention it here too, when you increase the friction, one thing that it does is that it makes rotation between the grains harder. Of course, everything is stuck together, like you have an old engine, okay, rather than a new freshly oiled engine. So one thing we've done is that we've simply prevented the grains from spinning, from rotating, by we can, of course, in the simulations completely prevent it. And we've done something which is a little more gradual, and we've increased the moment of inertia. So this is entirely artificial, but in that way you can further and further block or prevent the grains from spinning, from rotating. And the more we do that, the better the segregation. So actually the first example I've shown you, I've cheated a bit, but this is there you go. In that case, friction is very high already, 0.8,
Yes.
and I believe here that the rotation between, well, the rotation of each individual grain was also hindered a bit more than it could be in real life.
Yeah, so that
absolutely.
mimics. Yeah. So that mimics as well a little bit of particle shapes, right?
Exactly. That's
all
another way
spherical.
of saying, okay, we're working with spheres, but if you had cubes, for example, or actual grains, it is much harder for them to rotate. You are right that in many cases, as you know, you can have a sort of a gear going on here. That grain could freely rotate, making that secondary grain rotate and so on. Of course, in real life, with anything that's not spherical, that doesn't work. So you're absolutely right. That's a simple numerical trick to mimic angular, rough shape grains.
Very good. Okay. So I think we don't have any further questions. Thank you very much, Nicolas, for your talk. I will
Well, thank you.
stop the recording.